so far? Um, okay. Okay, so today we are going to talk about estimation a little bit and about statistical estimation. Okay, so first of all, let us recall the homework, right? So the homework was, see, so it was 2nd of December. Okay, numbers 3 and 4 on page 62, right? So these were the homeworks. Now I have to say that I have not received any attempts, but I think it's important that we here at least discuss them. Okay, so let's start with number 3. So if you are only told that you scored an 80th percentile, do you know what it means, basically? How it was calculated and what it means? So what do you think it means? Right. So that's actually correct. So actually, so with single caveat. So it's not clear, like from this description alone, whether you are like 80% of people scored like this or better, or whether 80% scored like this or worse, right? Because sometimes, so it depends from what ordering do you take, right? Because sometimes it's taken to be like the good thing, and sometimes it's the bad thing. But the idea is correct that basically you are, so you can divide your population 80-20, and your results are going to be on this division. So whether from a good side or a bad side, it may depend a little bit on the context. Okay, but in general, it's correct that so it may be right. So okay, good. So let's consider 4. Um, Okay, so what do you think? Okay, so I'm not going to read it out, right? Because you can read. Um, okay, so we have the study, and then um, we have math practice, and we have uh, interleft practice or spaced practice. Um, okay, so um, okay, so you see that these are our conditions. So um, what do you think are the problems that relates to the generality of the results? So whether we can so this is just one thing. So uh, it is said that the results are generalizable if you have your sample uh, somehow purely so truly random and non-biased, and then you can really kind of from this sample you can generalize the results to the entire population, right? But right, so so what do you think is a possible answer to this question, that um, whether the results are going to be generalizable um, to the total population uh, of students, right? Uh, okay. Yeah, so I think that's true. So you have, this is definitely a problem that um, if you just have volunteers, then okay, and then it's about study. So it may be that some kind of students would be much more likely to volunteer, right? So you don't have your sample is not going to be representative in the sense that it's not going to reflect the structure of the entire population. Um, and then you also have that subjects are not randomly assigned the test, assigned to not randomly assigned like math practice and uh, space practice, right? Uh, so this is also a problem, but you think it's a little bit less important problem, right? If I understood you correctly. Right, right. So it's already bad. So so the second choice doesn't really matter, right? Because you cannot make it at this stage. You cannot make it good already, right? So yeah. Uh, so yeah, I would also agree to this, and of course this is also so the second point is also bad. Uh, but you can say that because the first choice comes first, right? Because you first somehow choose the subjects, then already it doesn't really matter what happens after because it's already biased. So So probably indeed the first problem would be more serious. Although the second one is also cannot be overlooked. All right, and by the way, just a digression, which is actually not relevant to our course at all, but it's relevant maybe to the things mentioned in this exercise. There was actually, there are a lot of studies on that topic. What is better, massed practice or spaced or interleaving practice? And so the mass practice is when you really try to learn things, for example, by reading and rereading and rereading something again and again. And you do it presumably in a short period of time, right? So, or maybe, so you just do day after day after day, or and then spaced practice is, as the name suggests, the practice when you kind of do something and then you don't do it and then you do it again and so on, right? So, right, for example, if you learn a language, then the mass practice would be that you try to memorize the words like every day for some time. And then the spaced practice is that you take breaks and then you go back and repeat. And so these topics, so it's actually not clear what is more effective. It was more clear, but these topics have been studied, and I recommend you the book where this is very nicely described. So what it's called. Give me a second. I will find how it's called. Yes, so the book is called Make It Stick, right? So, and this is just, I think, a very good book, which actually kind of sheds light on how you learn and what are the more effective ways of learning. So I would highly recommend you to check it out. So once again, it has nothing to do with statistics. Well, except of course they use some statistics in the studies that are mentioned in this book, but you don't need actually to go into statistics. So I would I would recommend for you to check it. I think especially for if you learn something by yourself, this is just a valuable um, book. And okay, so good. So that was the homework. And so last time we discussed a little bit the foundations of statistics, and we discussed the hypothesis testing, right? In particular, the null hypothesis. And today we're going to discuss estimation, which is probably this is the things that you would that comes to mind when you just mention the word statistics, right? So that somehow you have some estimation of something, like, and then you have some errors maybe, right? And if you look at the press, so if you read something somewhere, you might come across that, okay, the poll shows that it has like something has like 36%, and the margin of error is like 2.8%, right? So these are the kind of things that we're going to talk about today. Okay, so okay, so in this, so we're going to follow the content, more or less the content of chapter 10 of the textbook that I sent you last time on statistics, right? I'm going also to share the screen. Okay, so okay, so so what are we talking about here? So here we have an example described the basic point, right? So okay, you have a certain sample of people, for example, 200 people, right? So the question you're interested in is like what fraction of the population supports building a new stadium, right? So you have, okay, to build a new stadium, not to build a new stadium. And then, of course, I mean, ideally you could ask all people, right? But this is expensive because you have to go and ask, or you have to organize a vote, you know, which takes money and time. So, and this is really, so as an alternative to that, you just ask 20 or 200 people, which is still maybe not necessarily very something that doesn't take any time, but it of course takes much less time. Okay, so you ask 200 people, and 106 of them said that they support the building of the stadium. So therefore, you have your fraction of people who support this project, right? And this number of 0.53 is an estimate, right, or point estimate of the population proportion, right? So you have So what are we talking about here? So you have the entire population of a city. So for example, in Wrocław, it would be actually, I don't know, let's say 700,000 people. And then you ask, okay, and then some of them support building a new stadium and some do not. And you don't know what is the real, the real proportion of people who do support it, right? You don't know. But, well, you might know approximately something, but okay, and then you ask 200 people and assume that it's really a well-managed sample, that 200 people are really chosen uniformly and randomly. And okay, 106 say yes. So you have 0.53, and this is your estimate, your point estimate for the proportion of people who support it, right? So it may be that the real proportion is, let's say, 0.45, right? So that 45% of the population supports, or it may be 55%, right? You don't know. But at least in your sample, you get this number. Now, okay, so you get this number. So of course, you cannot exclude reasonably the values that are close. Right? If you think about what is the true value, right? What is the value for the entire population? Now, it may well be 50%, it may be 51%, 49, 54, or and so on, right? However, actually, with high probability, or you can, so this is not quite correct, but you say that this is very unlikely that the value would be, for example, 30%, or that it would be 70%, right? So for this example, we'll actually see how unlikely it is. But so this, even those 200 people give you already some information, right? So, okay, it's not, you don't know like everything, but you can definitely say that it's very unlikely that the true value is, let's say 70%, right? And then but we will also look a little bit into this example in particular, how unlikely it is exactly. Okay, right. So the way it is usually done is that you have a confidence interval, and the confidence interval is equivalent also to the margins of error, right? So you can, in let's say in the popular literature, so I mean in the press, let's say, you would more likely to read about margins of error, but these are the same things, right? So confidence interval is the same as the margins of error in this case, right? For the purposes of statistical point estimates, right? Because margins of error has other meanings outside statistics, right? So, but for our purposes, they are the same. Okay, so, and for example, so typically the confidence interval will be a symmetric interval containing centered at the point estimate, right? So what does it mean? That here you have point estimate of 0.53, right? So then the confidence interval, so with some method, which we are going to discuss also a little bit later today, might give you these values, that the confidence interval is from 0.46 to 0.60, right? And you see that this is the interval which is centered at our point estimate of 53, and then it has so it has the length of 14 points, right? 14%. Now, and in this case, you have so what is usually said is that you have 50% with a margin of error 7%, right? So it means 53 plus minus 7. You might also see something like this. Okay, it means that it is likely that the real value in this interval. Now, what does this exactly mean? We will also talk a little bit about this today. Okay, so now for statistics, what is important that you have for statistical estimates that you have a notion such as degree of freedom. Now, we're not going to discuss it too much today. I will just note that the only way it comes out in more, let's say, elementary statistics. Let's for now focus on two things. So we want to estimate the mean value, right? And in particular, a typical problem would be, for example, the height in the population, right? If you have population of a country or population in a city, so you ask yourself, you can ask yourself, okay, what does a typical height of an individual? And then here, once again, you can just take, let's say, a sample of, let's say, 200 people, and you measure the average height and say, okay, the average height that I have measured represents kind of the entire population somehow, or and then you also provide a margin of error. Okay, so you can ask what is the average height, the first thing, and the second thing, of course, you can ask what is the variance, right, of the height. And so, for example, the variance within the population, so this is the same variance that we talked about during the probability course, remember? The difference between the square, the expectation of square minus square of the expectation, right? This is the variance. Now, the variance represents, well, as the name suggests, so to say, the amount of variability present in the system. And so now the variance and the variance plays an important role in kind of in the way you can view the variable that you're working with. For example, if you work with height, your variance would not be too high. But if you, for example, work with wealth, then the variance would be higher. Also, and the way you can see this is that well, you typically would take the ratio of the variance to the square of the expectation, right? And then so let me this will be very short. So if you have the right, so if you have if the variance divide by the square of the expectation, right? So you have this value. So if this is small, then kind of your individual observations are mostly explained by the mean, right? So for example, in case of height, now in case of height, it's not so small, but it is not large, right? So Actually, I don't know exactly what this is, but it's definitely not very large. So most of the height. So um, if you choose an average person, right, at random, then okay, and ask what is their height, right? You can take the average height, and then you add a small correction, random correction, and this should be approximately their height, right? Uh, so this is for the height. However, for something that has a really high variance, like for example, the wealth. If you take an average person, actually, so if you take random person, your average over the entire population tells you very little because variability is so great, right? So um, uh, but basically, you get practically no information about the individual from the mean value, right? Okay. Uh, okay, so but talking about the degrees of freedom, so here we have so this is basically um, roughly speaking the number of parameters that you can use, and and the idea is that the degree of freedom, roughly speaking, equals to the number of your observations minus the number of things that you estimate, right? Okay, and we actually don't need this. We only need it for one thing. And I think it's a little bit, okay, so I think uh, I will skip a little bit. Um, okay, so, okay, doesn't matter. So basically we need it for one thing. Now, if it, so we consider the the estimates of two types, right? Either the average, for example, the average height, or you can also consider the average wealth, and the variance, right? And so, okay, so to take the average, this is kind of clear what you do, right? So if you have uh, your sample x, right? X is just a sample of numbers, right? For example, 1.72, let's say meters, right? The height in meters, 1.64 and 1.88. Okay, so just a sample of three, which is not a large sample, but okay, let me just do it in centimeters, right? So we have 172, 164, 188. So we have a sample of three. Now, the sample mean and the estimate for the mean, of course, would be just the average, right? And this is, I think, clear, and I think this is intuitively clear that, let's say, if like the estimate for the mean is going to be uh, just the sum of xi, right? Let's say this is x1, x1, x2, x3, and this is right divide by 3, right? So by the number of elements. Now, and also please know this notation. This is a very common notation. If m is the true mean, so m is the true mean, and then you have m hat. So you have this hat here. It is it denotes an estimate. Okay, so this is an estimate, and this is the sum, the summation sign. So okay, okay, so this is, I think, clear, right? But for the variance, and this is important, for the variance, you take here n minus 1. So for the variance, if we want to estimate the variance, let's say, so what we would take the sum of xi minus this m thing and divide by 2, right? Not 3, but 2, because we should divide by n minus 1, right? Okay, so in here for square, right? Because it's for the variance. And this is the estimate for the variance. Okay, so it is possible to show that this is, of course, that this is an unbiased estimate. We will talk a little bit what it means. So this is the proper way to estimate it. Now, and why do we take here 2 instead of 3, right? You might ask, why do we take here n minus 1 instead of n, right? So one way to think about it is that somehow, because m itself here, right? M is the estimate for the mean. Because m itself is an estimate, somehow 1 degree of freedom was eaten somehow by m, right? And so you have a little bit less information because of that. Because okay, so somehow 1 degree of freedom goes there, and therefore you divide by n minus 1, right? Because you have this additional estimate here. Now, if you know true mean, I have to say, if this was your true mean and you know it, which is rarely the case, I should say, then actually you can divide by n here. However, because m is also an estimate, you divide by n minus 1, right? And in this case, you divide by 2. And another intuitive way to see that is that imagine that you have just one observation, right? One observation tells you absolutely nothing about the variance. Because, okay, what is if you have one observation, maybe it's just the constant, right? So you know absolutely nothing about the variance. And therefore, you cannot do anything with one observation, right? So it doesn't work for n equals to 1. But with two, you need at least 2 observations to be able to say anything about the variance. I mean, which is reasonable because the variance shows you, well, the variability. But how can you say about variability? You have just one observation. You have nothing to compare to. You have no way to talk about variability really. So you need at least 2. And okay, so in this somehow hints that here is n minus 1, that for n equals to 1, it just doesn't work. Okay, so let's now have a break. See you in 10 minutes. So let's talk a little bit about the properties of an estimate. So the 2 properties of an estimate are bias and variance. Okay. Okay, so here we have an illustrative example here. Imagine that you have two different scales and you would like to weigh yourself. So okay, so you have so imagine, so you consider you have two situations. The first, that you have a high-tech digital scale, and it varies very little from observation to observation. However, because it's just not well calibrated, it produces error on ever, and it let's say increases your weight by, let's say, 1 kilogram, right? So let's use the metric measurements. Now, and then you have another scale, which is just, I mean, a normal scale, which, like, you know, mechanical scale, and it gives you different results each time with much higher variability than 0.02. However, on average, it is accurate, right? So we have here two different somehow sources of errors in our estimate. So the variable that we have is our weight. And then we can take as an estimate a single result of of a process of weighing yourself, or you can take, actually you can weigh yourself 10 times, right, and then take the average. It's either way, you could take either of those, let's say. Okay, so for scale 1, what you have is you have high bias, what is called high bias but low variance. Now you see that you have low variance in the sense that the results are very stable. However, they are also off, right? The results, the observations that you obtained do not correspond to the correct value, and so this produces a bias. Now, scale 2 has large variance, right? Because you have, well, just how it is described, it has large variance. However, since it is said that on average, it produces an accurate result, it has low bias or no bias, right? Or let's say actually low bias. And so these two things illustrate two different sources of error, so to say, that can occur in an estimate. Now, arguably, in this example, actually, the scale 2 is preferable because you can make a large number of observations, right? And then this is going to reduce your error. However, however many observations you make here in scale with scale 1, you're still going to have this bias. Okay. Okay, so, and let us now consider an illustration. So this is just, now I have to say that these notions, bias and variance, are key in machine learning and predictive modeling. Okay, so, and they're used extensively, but here we just use it as an illustration for our example, or it can be any example. So this picture illustrates the difference. Now imagine that you make a point estimate And so far we have discussed only basically sample mean, right? When you take certain sample and you take the mean. But actually, your point estimate can be defined in any possible way. There are so many ways you can define. For example, just to give you a flavor, imagine that, okay, you want to estimate the average height of the people in a city, right? And imagine you take a sample of 10 people. Now, as we said before, you can just take the average of the sample average, right? The average of the sample, and use this as your point estimate. Okay, and that is a reasonable thing to do. However, for some reason, you can say, okay, I just take the height of the seventh highest person, right? So, or let's say the fourth highest person, right? Let's say you take the height of the fourth highest person as an estimate. And this is just your estimate, right? So it's not, okay, and so you can combine your estimates in any possible way, right? So estimate is just, let's say, a function of your sample, right? It can be any function a priori. For example, if you have a sample of 10 people, it can be just the height of fourth highest person. And this is also an estimate. And it's not clear a priori if it's a bad or good estimate, right? So you have to consider it. Okay, but imagine that, let's say you have your estimate, right? So you have your exact value, which is in the center of the circle, right? So let's imagine this. And then you have your estimate. And of course, the estimate itself is random, right? Because the estimate depends on the right. For example, if you have your estimate, let's say h for height, right? It is a certain function of your sample, right? So, and x is the sample, right? So once again, typically you would take the mean, right? You would take the mean typically, and in this case, f is going to be the mean of x, the mean value. Or you can take something else. For example, the height of the fourth tallest person, right? Then it would be different f. But so either way, h depends on your sample, right? And then this sample is random, right? You assume that you have your sample uniformly without replacement from the population. Right? Without replacement means that you have 10 different people. You cannot have, let's say, 10 people, but 3 of the people are the same. So that means, right? So your estimate depends on your realization of your sample, right? And for different samples, you're going to have different estimates, which is natural, right? Even if you think about the sample mean of a height, right? It may be just by chance you have some high people and then you just have a high number, or you have low number. I mean, it's possible. You have some variability. So now the estimate is considered to be and okay, those 4 pictures illustrate the differences between low bias, high bias, low variance, and high variance, right? So here we have our estimates. So our estimates are blue dots, and the true value is in the middle of the circle, right? So we see that our estimates are all very close to the true value, and also that somehow the variability of our estimates is not too high. It means that our estimates are more or less concentrated, right? So we have low bias and low variance. And this is actually the ideal case scenario, right? This is the best case scenario for any model. Of course, this is hard to achieve. Now let's look at this picture. You have here low bias, but high variance. So what does it mean? So your estimate, which is, remember, itself can be seen as random, just a random variable, right? for example, so X is a random sample, right? So X is a random collection of individuals, and therefore H hat is going to be a random variable. So we see that this random variable has high variance. However, on average, it gives the value which should be close to the true value, right? So we have high variance, but we still have low bias because the average is, yeah, more or less where it should be. Now here we have high bias and low variance. So here we have, you see that your estimates are concentrated, right? They're, I mean, they do not vary too much. However, they are off. They are off the mark. They're not very accurate. So you have high bias, right? But low variance. And then this case, which is probably the worst case scenario, when you have high bias and high variance, where right, so you have so your estimates are scattered, right? Which means that they have high variance, but also they're also off on average. So the average is also way off the mark, right? So the average is not correct either. So you have high variance and high bias, and this is somehow the worst case scenario. Okay, but of course this is also quite bad because for practical reasons it's also nothing, not really what you want. Okay, so these are the properties of an estimate. So you have bias and you have the variance. Okay, so right, so in these textbooks, what I call the variance is called here sampling variability, right? So maybe it's a more suggestive name because you have kind of from sample to sample, you have a little bit of a difference, right? Okay. Now we come to the confidence interval. And so this is, you remember, we talked a little bit at the beginning about that. So that we had confidence, so we had margin of error. So today, earlier, we talked a little bit about that. And now we're going to consider this more in detail. Okay, so and how it is computed. So okay, so we are going to consider only the simplest case. So, but then we're going to discuss about more general parameters. But we will start with the simplest case when we have a fraction, right? Okay, so I'm going to stop video for the moment. Okay, so we come back to the Okay, so let's go back to the first example that we considered today. Remember, we have 200 people, and then 106 said they support the proposition. Now, and then we have a confidence interval of 95%, and the margin of error turns out to be 7. So what does it mean and how this margin of error is computed? Now, it is typically computed with t-distribution, and we will talk a little bit about this in a moment. However, in this case, well, let's just see how it can be derived in principle, and then so we will talk a little bit about more the details. Okay, so you have so you have 200. So you have 200 of the size of the sample. So the sample of the size 200, and all right. So and then you have n equals 200, and we have let's say our random variable x equals to 106, right? And x is the number of positive answers that we get. So now we're just going to talk about the principle. Now, since you have many people in a town, right? In a city, and you can say that their opinions are more or less independent. Now, it's not absolutely speaking, this is not true, because okay, if you have a family, maybe, or friends, they have, of course, some dependency, but it's a reasonable assumption in this case for all intents and purposes, because you don't have thousands of friends to influence anything on a significant scale. You just have a couple of people. So either way, so we assume that every person has a probability of having a positive opinion, right? And this probability is p, right? And this should be, of course, this probability equals to the fraction of people who have positive opinion, right? So who would answer yes. So we have an estimate of p, which is equals to 0.53. Now, we don't know anything about p. However, what we know that bx follows approximately a Bernoulli distribution, right? Bernoulli distribution with n equals to 200 and p equals to p. Okay, right? So now we don't know this number, but we know that x is somehow sampled from the Bernoulli distribution, right? So the way to determine the confidence intervals, right? So let us denote for a p, let's say yp. Okay, so let me just write where b and p is the Bernoulli distribution with 200 with n trials, and and the success probability. And the success probability. P. Right? So this is just a reminder. B and P. Remember, so the Bernoulli distribution is the sum of n independent random variables, so n independent coin tosses, each having success probability p. Okay. Okay, so now 95% confidence interval is or let's say consists of values of p such that, okay, so, and here here is basically the definition, such that the probability that this Bernoulli random variable minus okay, so so the probability that all right, so the probability that so I should of course, so here we talk about the averages, right? So I should divide by n, right? Because right, so okay, so we'll say 1 over n, and then I take the absolute value, that it is greater or equal than p minus our estimate is so this probability should be less than 0.5. Okay, so let's have a further look. Okay, so let's just talk about it. So what does it mean? So you have your sample and you take the mean, right? So this is your sample mean. And of course, the expected value of the mean is p. Now, of course, you expect to be some deviation, right? However, what you want it to be, you want the deviation to be small, right? and in particular, you only consider the values of p here, such that this deviation is very unlikely. That the deviation of this size is unlikely. Okay, so in other words, the probability that your sample mean is going to be in this interval is going to be in this interval, which is given by okay, I can denote by this, like this. So because we don't know whether p is greater than our estimate or smaller, right? So I take the differences and then I take the absolute value. So I have this interval, right? And so this probability okay. So the probability that your sample mean is going to be in this interval should be larger than 0.5, right? So, and this is basically, yeah, this is how you can maybe it's a little bit simpler to look at it. So let's just consider an example, right? So how do we determine whether p is in this interval or not? So let's think, we just take p equals to this, right? Then let's say we have a yp equals to Bernoulli random variable with n and p with n tiles, so n equals to 100, and p equals to 0.56, right? Okay, so this gives us a distribution, and then we ask ourselves, what is the probability that right. So here, of course, the interval should be centered around p, actually, right? Because p plus, right? Because here will make the difference. What takes the difference is p. So here it should be centered around p. So what is the probability that 1 over n of this number is going to be in the interval? Now, what is the interval? The interval is going to be 0.56 minus 0.03, right? So the difference between p minus p hat is going to be 0.03. Here you have 0.56 plus 0.03, right? And so this equals to the interval 0.53, 0.59, right? And so you ask, what is this probability? And of course, you can actually compute this probability, right? Because this is a binomial random variable, so we can actually compute it. And it turns out to be, of course, this will turn out to be bigger than 0.05. And so this value is going to be in our interval. Okay. So you see that, okay, so maybe these formulas, they're a little bit not very intuitive, but I hope that at least this, if you take a specific p, it gets a little bit more intuitive and more understandable, right? Because, so you have p, and you take the difference, right? And then, of course, you see this interval. This is easy to kind of imagine, because, okay, so here's your line. So here you have your estimate, and then you have P, right? So you just take this interval. You take here, and then you take the same distance to the right. Right? So you have this interval. And then you consider what is the probability that, assuming that the average is P, right? This is your sim. What is the probability that this sample, the average sample mean, is going to be in this interval? And you just look whether it's bigger than 0.5, 0.05, or it's smaller than 0.05. And if it is greater than 0.05, then it does belong to the confidence interval. If it is smaller, then it doesn't. Okay, so this is the definition. So let us now stop here. For now. So, and after break, we're going to continue and see how it can be computed approximately, this interval, which actually may be easier. Of course, this is much easier than by this definition, which is very difficult, right? So we'll see how it is, because you would need to do it for all P, and this is, or you like, this is not easy. But we'll see how it can be done a little bit in a simpler fashion. So I suggest we meet in 20 minutes, and then we finish earlier. Is it okay? Okay, so see you in 20 minutes. Well, and to do so, we first need to talk a little bit about the t-distribution. So this is a distribution. It has a formula, but it's rather complicated, so it doesn't matter. So the t-distribution is also called t-student distribution, or just student distribution. Now, student is a pseudonym, so it's not student as you are students, like, but it's kind of like a name, but it's not a real name. But okay, so, and this is approximately how it looks like. So the blue line here is the normal distribution, which is, okay, this is a normal distribution, and then a t-distribution with different degrees of freedom. It's a little bit more concentrated. Right? Okay, so but they all look pretty similar, right? You can say that the normal distribution is t-distribution with infinite number of degrees of freedom. Or if you have many degrees of freedom, you can basically normal distribution. Okay, so we're not going to talk about the properties of this distribution, but it can be computed, the values can be computed via software, which we will hopefully do. Okay, and now we will see how it relates to the confidence interval. Now let's start from an example. So imagine that you have, okay, you have weights of 10-year-old children. So the weights are normally distributed with a mean 90. So it's probably in pounds, and standard deviation is 36, right? Because so it's 90, it's really high. I hope, right? So in kilograms, so it's probably in pounds. Okay, so let's just stick with the numbers, 90 and 36. Now, what is the sample distribution of the mean of a sample size of 9? Okay, so let's see what we're talking about here. What is the sampling distribution of the mean for a sample size of 9. So we have a sample size of 9, and then from the sample size, we have the mean value, right? And what is the distribution of this mean value? Okay, so let's just write a little bit. So you have 9, right? So you have sample size of 9, right? So your mean value is going to be, so let's say xi normally distributed with mean 90 and the standard deviation 36, or is it standard? Yes, standard deviation 36, so 36 squared, right? So this is just means that normal distribution with mean 90 and standard deviation 36. So what is the distribution of x1 plus x2 plus and so on plus x9 divide by 9? Okay, so let's say we cannot, of course, we could compute it directly, but this might be difficult. But we can compute the mean and the expected value and the variance, right? So the expected value, so let's denote it by y, right? So we denote this by y, and y is the sample mean, right? So you have the sample, right? X1, X2, blah, 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 X9 considered a sample. And then you have a sample mean, which is Y. Okay, so the expected value of Y equals to 1/9. And you remember that the expected value of the sum is the sum of the expected values, right? But they are all the same. So it's going to be 1/9 over 9 times the expected value of x1, which is going to be just the expected value of x1, which is 90, right? Now, and here comes the variance, which is a little bit more interesting. The variance of y variance of right? Now, you remember the properties of the variance, that the constant comes out with a square. So this is going to be 1/9 square times the variance of the sum, right? And then from here, you remember that since the variables are independent, the variance of the sum equals to the sum of the variance. So this is going to be but then they're all the same. So this is going to be right. And so this is going to be 1/9. Now the variance of x1 is 36 squared. Remember, we were given that the standard deviation is 36, right? But the variance is equals to the square of the standard deviation, right? So we have, and this equals to 12 squared, right? At the end. Okay. So the standard deviation is going to be 12. The standard deviation is going to be 12. Okay. Okay, so and this is how the distribution of the sample mean is going to look like, right? So this is the density, the plot of the density, and then the shaded area represents 95% confidence interval, right? So now you remember this is the density of a continuous random variable. Integral over the density equals to 1, right? Now, if we just take the shaded area, integral over the shaded area is going to be equal to 0.95. So it's going to be 95% of the total mass. Okay, and then you see that 95% of the distribution lies within these boundaries, and then you have this factor, right? That and then, okay, look at this statement, right? So that if we repeatedly compute the mean from a sample, right? So if we compute the sample mean repeatedly, and create this interval, right? So this interval, and 2352 comes from here, right? Then this interval, which is, by the way, the shaded interval here, this interval is going to contain the sample mean 95% of the time, or the population mean 95% of the time, right? Okay. And this gives you the formula for the confidence interval. Okay, so let's look. So M is the sample mean here, right? So you don't know the real mean, but this is a sample mean. Now, sigma M is the estimated variance, which in this case we know, but typically we have to estimate it. But okay, so this is the variance. And then Z.95 is the so plus and minus, well, in this case, yeah, it's the same. So this is the quantile of the distribution. And they can be, you can obtain them from the program, actually. We'll look a little bit how to do it in a moment. Okay, and this is your formula. Okay, so okay, so we're not, of course, going to derive this because this is also quite involved, but so let's just use it on the example that we had at the beginning, right? Remember, our sample mean was 0.53, right? Now we need to estimate the variance. And okay, we can estimate right, so it was M, or we can estimate the variance. So remember, we had N equals to 200, right? And the outcome was we had 106 successes. We had 100x successes. So remember, that was the first example we considered today. So we're now going to derive the confidence interval using this data, and just to see how it is done. So okay, so we have the sample mean. Okay, so the sample mean is 0.53. Now we need to estimate the variance. So we need to estimate the sample variance. And remember that the sample variance, okay, so let's say we have Xi1 plus Xi200, right? And we know we observe X equals to 106, right? This is what we know. So X is a Bernoulli random variable with, so we can represent it like this. So what is going to be the variance of X? Okay, so in this case, we're talking about the sample variance. So, okay, so an estimate of the sample variance, once again, we don't know because we don't know the true value of P, right? So P we don't know, but we want to get confidence interval. So the sample so what we take as an estimate is going to be so we can so we're going to take xi minus the mean square times 199, right? You remember 200 minus 1, so 199. Okay, so this is going to give us 106 times okay, so we're going to have 106 1 minus 053 squared, right? Plus right, plus 94 times 053, right? 0 minus 053, because we have 106 values are 1 and 94 are zeros, right? So this is why I write it like this. And then here, actually, we have to so this is going to give us an estimate of the variance of Xi, right? So, but then we're still going to have to divide by by the square root of 200, right? So, okay. So this is going to be like this, right? And then this is going to be what? So it's going to be okay, so let me just say that this is going to be so of course we can confuse it with like in a software, but I'm going to use a shortcut, and I'm just going to say that this is going to be approximately it's going to be approximately 0.53 times 0.47, right? Okay, so this is going to be an estimate of the variance. But this is just the variance for a single thing. Now to estimate, all right, and so it's important to say, so let's say we estimate the variance of x, right? Then actually we don't need here to divide because x is at the sum, and we just take this expression. So this is going to be this times 200 approximately. Okay, it's going to. Oh. So it's important yeah. So it's important to keep in mind what variable we want to estimate the variance of. So let's start with just x, right? And x is the sum. So we can take it like this, right? Now it should be actually, we should divide it by 109, so it should be 199 here, but let's just take 200. It's a really small difference because it's a large number. Anyway, it's approximate. Okay, so but then we take the average of x, right? So and if we take the average, the variance is divided by 200 square, right? Because we have, right, remember that the variance of Cx equals to C squared times variance of x, right? So if we take, then we take C equals to 1 over 200. And then, so let's denote y equals to x, or 1 over 200 times x, right? So let's denote let y be this thing. And in this case, the variance of y, okay, I will write like this, okay? Variance of y. So it's going to be 1 over 200 squared variance of x, right? So this is going to be this product divided by 200, right? Because it was multiplied, now we divide it by square of 200. So this is going to be the variance of y. Okay. Okay, so we now have, and this is the variance that we need. So y is the sample mean, right? And we need the variance of the sample mean. And this is this variance, right? And remember, so the formulas are for the confidence interval. So I'm just thinking what letters to use. Let's say okay, let's say U plus, or let's say confidence interval plus, which is the highest. So you take the mean value, which is in this case our estimate, our average P, plus we take the quantile of T distribution, right? Which was denoted as, what was it denoted as? Okay, okay, so let's just denote by Q. And you take 0.95 quantile. So this is a quantile, and we will talk a little bit in a moment how to get them. And then we multiply by our sample variance, which is this number then, right? Which we just computed. Sorry, you multiply by the standard deviation, right? You don't multiply by by the variance, you multiply by the standard deviation. So it's square of the variance, right? So this is also important here. Okay, okay, and now, so we have this number now, and this is the right boundary of the interval, and then confidence interval left hand is the same but with minus. Okay, and now, okay, so we have this number we have, right? This we have, this we also have, and this we can obtain from a software. Okay, so now we can just compute it. So let me just compute it. So just a moment, I'm going to open everything. Okay. See. Okay, so this is going to be our so we have, so let's say we have p hat equals to 0.53, right? Then we have let's have just sigma equals to, so we had 0.53 times 0.47 divided by 200, and then square root. Right, so that was this is our variance, and then now the quantiles of the Q distribution you can find as QT, right? So okay, so in this case we need 0.95, and then the degree of freedom is we're taking 199, right? Okay, this is our quantile. Okay, so, and now we can, we're ready to compute everything. So we take p hat. So let's compute the upper bar, p hat plus, so we take sigma times qt, one more thing. So this is a little bit tricky. So we actually have to take 0.75 here, right? Okay, why 0.75? So let me just make an illustration. So imagine this is your distribution, right? you want to take the area such that this shaded area is 95%, right? You want to take this number, these two numbers, let's say alpha and minus alpha, right? This area is 99. So how to fill? Oh, that's nice. So that this area is 99%, 95%. Or maybe let me just go to an image. So this shaded area is 95%, right? However, it means that if this is the quantile, and what is below, so to each side you have equal amount. So you have 5 divided by 2, 2.5% to each side, right? So you have here 2.5% of the mass, and here 2.5% of the mass. And in the shaded area is 95%. So this number, to the left of this number, you have 97.5% of the mass, and to the right you have 2.5. So this is why you take here 97.5, or you have 975, right? And this is going to be our estimate. And then df. Okay, so you see, this came out to be our confidence interval, our upper value. And then the lower value we obtain in the same way, but with the minus, okay? And this is, yeah, okay. And you remember, these were exactly the values that were also reported, right? Basically, we have 46 and 60, right? And then here we have very close, right? So, but of course, you don't write all 5, I mean, all 5995. You just round it up to all 6. Okay, so this is exactly how those these values are obtained. Right? Okay, so let us reiterate a little bit. So first, let us, let's say, revisit. All right. So first thing, find the sample mean. Second, find the sample variance. And then third, their confidence interval is, okay, so let's say I denote this by M. Find the sample mean M. Find the sample variance I should stop sharing. Find the sample variance, let's say sigma squared. And then the confidence interval is going to be given by so you take your sample mean and then take plus minus. You take the quantile of okay. Okay, I will saying a little bit what it is, and you take the sigma. Right? And please note that here the variance is sigma square, right? And sigma is like the so we take square root here. Okay, and then let's say the confidence interval gives you 1 minus alpha percentage of 1 minus alpha percent confidence interval for the mean. Okay. Here Q1 minus alpha over 2 is the 1 minus alpha over 2 quantile of T distribution, of student T distribution, of T distribution. So let's say of student T distribution. All right, so now that was so today. So I want to say that this topic is, of course, not obvious, so it's not trivial, and I fully realize that. So I have to say that this kind of questions is not going to be on the tests, right? And of course, we're a little bit rushed because, for example, I didn't properly introduce the quantiles. And of course, ideally, we would talk more about the sample mean and the sample variance. Right, and as I told you that, ideally you would have, right, but okay, so it was a little bit rushed, but hopefully you got the idea, just the idea and the feeling of how these things are computed. So now if you see something that you have this number with this confidence error, or with this margin of error, you actually know at least how it is computed, right? But now we are going to talk a little bit what it means, a little bit more. We're going to talk a little bit more about what it means, and then we're going to finish. So this is how it is approximately computed now for some. So this is for, let's say, simpler tests. For more complex tests, this confidence interval is computed, maybe computed in a little bit different way, in different ways, but okay, so but the principle remains the same for many tests, right? That you have some kind of, so you take the mean, then you take some kind of a variance estimate, and you take some kind of a quantile, and this is confidence interval. Okay, so but what is it supposed to mean? Okay, so a naive interpretation is that the probability that the true value of across the population is in this interval, right? So I would like, so in our example, the true value of the true value of the fraction of people who support the building of the stadium, right? Remember, we're talking about the building of the stadium. So now this true value is in this interval with probability 95%. And this is a kind of common interpretation, but this is in fact not accurate. So this is not correct. Okay. What it means is it says that for every value outside of this, so or rather what it means is that if the true value outside of this interval, right, if you take a value outside of this interval, the probability of getting your sample mean 50 or 53 in a sample of 200 would be below 5%. So let me just write it down. So the meaning of the confidence interval so for every p outside the confidence interval the probability of getting the sample average or the sample mean, right? So this is what we're playing. We're playing the sample mean 0.53 in a sample of the size 200 would be, or I can write is below 5%. Now I need to add one more thing. So 0.53 or further away, or further. Let me just add here, or further. Okay, and let me now just illustrate. So imagine that. Okay, so this is your line, right? And then you have here 0.53. Now imagine that the two. Okay, so you have here the confidence interval. Let's say here you have 0.6, and then here you have 0.46, right? This is your confidence interval. It's here, right? So let's make it symmetric. Now imagine that the true value is here. Let's say 0.65, right? Now, actually, we don't know what is the true value. But imagine if this is a true value, right? So the probability, so if this is true, but you observe 0.53, so you have a decent discrepancy, right? You have 0.65, you have 65%, but it is the true value, but in the sample you have 53%, right? Okay, it's a reasonable discrepancy, but what the confidence interval tells you that if this is true, then the probability that you obtain this number or further, you see, or further from the mean, let's say. So like the probability that you find yourself here, right? So if this is our true value, and okay, we assume for the moment that it is, then the probability that you get this result or below is going to be less than 5%, right? So
let me just replace it with smaller than. Well, below is also okay. So you don't need to replace it, but it's just okay. And the same goes for the other direction, right? So I just draw the same picture. And then if the true value is somewhere here, right? And the probability that you are going to find yourself here is going to be below 5%. So you are unlikely to deviate as much. So now what conclusions can you draw? Now, it doesn't mean that this is not the true value, for example, in this case. It may be that, yeah, this is just, I mean, by randomness, 5% is not too small. It's not impossible to have an event which is, it's 1 in 20, right? And 1 in 20, it does occur, right? If you have every day 5%, then within a month, you are more likely to have some event, right? So, however, it may be that you either have to, maybe this is not your true mean, or either way, in realistic scenario, you don't know what is your true mean, right? So the realistic scenario is that you say that, okay, most likely my true mean is going to be in this interval, because if it is outside this interval, I would be very unlikely to observe what I have observed, right? So, and this is kind of, if you want, the philosophy behind the confidence interval, that if you're outside this interval, you are unlikely to observe what you observe. I mean, it's not impossible, but it is unlikely. And this is where it kind of comes from that it's confidence. So, like, if you're outside this interval, then you would observe such a large discrepancy in 5% of cases or lower, right? So it's not impossible, but okay, so it's not very likely. Okay, so if you have some questions, then you can ask now. Otherwise, we're going to finish. So I'm going to just tell you what is going to be. So the next week is we're going to have a little bit a more easygoing class, and we're just so it's not going to be, let's say, any really material, but we're just going to look into some stuff that is hopefully going to be illustrative and interesting, hopefully. Well, maybe not not extremely exciting, but yeah, hopefully something. Right, so first it's going to be one day before the break, right? I think. Oh no, it's going to be our last meeting. So yeah, this is why. Right? Our last meeting this year. Okay, so if you have some questions, you can ask now. So there will be no homework for today. Now, if you would like to learn more about the distribution, about the confidence intervals, I suggest you to read this chapter chapter 10 in this book. So it's, of course, I skipped some explanations, but of course, they also rely on some other things that we haven't covered, right? So, okay, so, but let me know if you would like to know more about the confidence interval, let me know, and I will maybe find something more elementary, or maybe that you can read or watch on your own. Okay, but this is not going to be on the test. Okay, so then if you have some questions, you can ask. And there will be no homework for today, okay? So if you have some questions, you can ask, but otherwise, we're going to stop now. I'm going to keep the meeting going, so you can still ask me questions if you have some, right? But so for the moment, then have a good evening and goodbye.
Thank you very much. Goodbye.